Ohm's law, we have already studied about the requirements of a circuit to conduct electricity. We have learnt that whenever a potential difference is applied across a conductor, a current passes through it. But what is the relationship between voltage and current? Mr. Spark would help us find out. We have a circuit with us. It has a battery of 1.5 volts, an ammeter which measures current, a bulb, a switch, and a conducting wire. Now we place a conductor in the circuit to complete its path. When we switch on the circuit, the bulb glows and the ammeter shows a reading of 0.15 amperes. We note this down. Now we replace this 1.5 volt battery with a 3 volt battery. When we switch on the circuit again, the bulb glows brighter and the ammeter shows a reading of 0.3 amperes. Can we see any kind of relation between voltage and current? Let us take a ratio of voltage to current. In both the cases, the ratio comes out to be 10. This was also observed by a scientist called George Simon Ohm. George Simon Ohm formulated the relationship among voltage, current, and resistance as follows. Current in a conductor is directly proportional to the applied voltage across its ends. Voltage is proportional to current. V equals constant I, V by I equals constant R. Where I is the current in amperes, V is the applied voltage, difference in potential in volts, and R is resistance in ohms. Let us take the analogy of water flowing through a pipe to understand how the three variables, voltage, current, and resistance, are interrelated. When you increase the pressure, the flow rate increases. Greater pressure implies greater flow rate. When you decrease the pressure, flow rate decreases. Flow rate also decreases when the resistance increases. Similarly, in a circuit like this, when you increase the voltage, the current increases. When you increase the resistance, the current decreases. In the first model, we observed that the flow rate of water increases with increase in applied pressure in the pipe when resistance remains constant. That is, flow rate of water is directly proportional to the applied pressure. In the second model, we observed that the flow of charge or current increases with increase in voltage. This implies that current is directly proportional to the voltage. That is, I is proportional to V. We also observed in the first model that the flow rate of water decreases with increase in resistance in the pipe when pressure remains constant. That is, flow rate of water is inversely proportional to the resistance offered by the pipe. In the second model, we observed that the flow of charge or current decreases with increase in resistance. This implies that current is inversely proportional to the resistance. That is, I is proportional to 1 by R. It is easier to understand Ohm's law using Ohm's law triangle. V equals R into I. I equals V by R. R equals V by I. Consider a conductor satisfying the Ohm's law in the form of a slab of length L and cross-sectional area A. Imagine placing two such identical slabs side by side so that the length of the combination is 2L. The current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab is identical to the first, and the same current I flows through both. For this combination by Ohm's law, V is I into R, which is I into rho L by A. Here, R is rho L by A, where the constant of proportionality, rho, depends on the material of the conductor, but not on its dimensions. Rho is called resistivity. In equation, V equals I rho L by A. I by A, or current per unit area normal to the current, is called current density. It is denoted by J. The SI unit for current density is A by M square. If there is a uniform electric field with magnitude E inside a conductor with length L, the potential difference V across its ends is given as EL. Substituting V equals EL in V, we get EL equals J rho L, or E equals J rho. This equation deals only with magnitudes E and J. However, it can be cast in a vector form. E is directed along the direction of current density. Moreover, J equals JE by E is also a vector. Thus, the vector form of the equation will be E equals JP, or J equals rho E, where rho equals 1 by P is the conductivity. Often, Ohm's law is stated in this form. Activity. To perform this activity, we take a nichrome wire of about 50 centimeters length and apply a potential difference of 1.5 volts from a battery. Then, we measure the current flow through the wire with the aid of an ammeter connected to it in series. Now we note down the potential difference across the resistance using a voltmeter connected across it. This set of reading is noted down and tabulated for a set of readings of I and V by increasing the number of cells. Graph between the voltmeter and ammeter readings shows a straight line pattern. This straight line indicates the voltage-current relationship and is known as Ohm's law, and is expressed as V is proportional to I, which implies the ratio of V to I is a constant.